All right, good morning, folks. Let's go ahead and get started. So, a couple of things that I want to talk about before we get into the lecture. The exam is Monday, and I promise everybody a review session at some point before the exam, and I sent out an email about that. So I need you all to respond to that email about what you all think would be the best opportunity for that. I can do just about any afternoon or evening this week. I don't think I listed Friday, but I could do Friday as well. And I could even do Saturday morning. I'm here on Saturday, so that's just totally up to you all. So respond to the email, let me know what works best for you, and I'll go with the majority rule. In review sessions, I don't cover anything new. I don't have any agenda when I come in. It's just answering your questions. So if you can't make it, I mean, you're not missing out on anything new. You just might miss your opportunity to ask me any questions. I also placed an old exam from 2006, which was apparently the last time I taught this class. So it is in the Canvas shell as well to give you an idea of how I ask questions. Now, there was a different book, different order of chapters, but I think you'll see some things similar to what we had. And I use what's called a zip grade form, which is like a Scantron, but I get to grade with my phone. So I take a picture of it and it grades it for me. So it's kind of cool. Be real quick with it. So there is a multiple choice exam, but there will be space on the exam where I ask you to write, to work out the problems. These are not problems that you're going to be able to solve just by picking what looks good from A to E or whatever, okay? So keep that in mind. And also the nice thing about that is I have had students that have written down the right answer, came back to me and said, I got this right, but instead of D, I circled E. Okay, well, you got the right answer there. I'll give you credit for it. So it's in your best interest to work everything out from start to finish. You will have the entire class period to do the exam. I write the exam to where the median student should be done in about 45 minutes. So you got plenty of time, okay? And any questions about the exam? Yeah.
How many questions?
I haven't decided yet. It'll probably be about what you saw on the example exam, and I think that was 25, maybe, something like that, questions. So somewhere along those lines. Some of them are going to be, easier for you to answer than others, so, in terms of what it requires you to do. And so, yeah.
You mentioned Scantrons. Do we have to get our own Scantron?
No. I bring, it's a zip grade form is what I use. And so basically, when you finish turning in your stuff, I just pull my camera out on my phone and I just click, and it grades everybody's zip grade. So you can use pen, I highly recommend pencil in case you need to erase something, but it will grade anything as long as it's dark.
25 questions, sir.
25? Yeah, that's about where we're going to be.
We're allowed notes, right?
You're allowed your handwritten notes. Print them out. If you take on a tablet, print them out and bring them with you. You are not allowed your book, but you are allowed your notes. And if you have a model kit, you're allowed to have a model kit. So I'll let you have all of that stuff. All right. Last time, we started talking about alkanes. And if we look at this one, I've got 1, 2, 3, 4, 5, 6. So what would the parent be?
Hexane.
Yeah, this is a hexane parent, right? So we've got hexane. We can put substituents along the way, right? And so if we were to put substituents, here and here, right, we would have to indicate the numbers. We'd have to tell what the substituents are, where they're located, right? So we went through all of that. For the purposes of the exam, I'm going to keep things to pretty small molecules. I'm not going to give you anything that's got 20 carbons in the longest chain, or probably even 10 carbons in the longest chain, okay? But it's certainly fair, 4, 5, 6, 7, something like that. So you need to know all of those parents. I told you through 10, but in reality, it's probably going to, not go all the way to 10, just because I also got to take into account the amount of time that it takes you all to work a problem. Now, last time we also started talking about things if we look down these single bonds, right, and we noticed that we can rotate. What did we call that? Conformations, right? And that's a different conformation than that, right? And what did we say? We said that big groups want to be as close as possible or as far away as possible?
Far away.
Far away, that's right. So this group and this group, want to be far away from one another. And that's why we get, this nice zigzag shape, okay? Is this saturated or unsaturated?
Saturated.
It's a saturated hydrocarbon. What does that mean?
Means it's
Maximum hydrogens.
Pardon?
Maximum number of hydrogens.
Maximum number of hydrogens for the number of carbons. That's exactly right. I can't put any more hydrogen on this, right? Now, what happens if I take the two ends and I connect them together? Now what do I have?
Cyclohexane.
Cyclohexane. Is that saturated or unsaturated?
Unsaturated.
It's unsaturated because every carbon has only two hydrogens, right? Okay, so this is an unsaturated hydrocarbon. We actually had to take two hydrogens off of the ends to connect them together, right? And so now we have cyclohexane, which is a unsaturated hydrocarbon. We also talked about these things that are pointing up and down. What did we call those?
Axial.
These are axial, right? And the things that are going around here?
Equatorial.
Equatorial. So it's like the axis and the equator, right? And so that's kind of, I think, where we stopped. Now imagine if I take two red spheres and I put one of them up here on the red, or on the axial position, and I put one over here on the equatorial position. So I've put a red sphere on carbon 1 and 2. Right? So this is 1,2 hyphen di-red sphere cyclohexane, right? We don't know what the red spheres really are yet, but they can be anything we want them to be. How am I going to tell people whether or not this one is on the axial and this one's on the equatorial? How am I going to name that?
Repeat the question?
How am I going to tell you that this one is on the axial and this one's on the equatorial in a name?
By labeling which, based on how many carbons there is, or which one is located on.
Okay, that's going to give me the location, 1 and 2. That's true. But how do you know
Direction.
when I say 1, 2, di-red sphere, cyclohexane, how do you know that this one is axial and that one's equatorial? You don't. You don't. So I have to put some other kind of prefix out there to let you know that this is the way that it is. This is where building models comes in very handy, because if I take this and I try to flatten it out, what do I know about those two red spheres? Are they on the same side of that plane or on opposite sides?
Same size.
They are on the same side. So we call that cis. Okay, so this would be a cis 1, 2, and that would be italic. Okay, di-red ball. Sounds like a drink, doesn't it? What if I take this one and I move it over here?
Will be on the opposite side.
And when I flatten it out, whoop, if I don't break my model, when I flatten that out, they are on opposite sides of the plane, right? So if that is cis, what do you think that one is?
Trans.
It is trans. Trans. 1, 2, di-red ball, cyclohexane. Why does it matter here?
Because if you don't tell you what if you don't label it right, it's going to be wrong.
Okay, that's true.
Because if you don't, okay. Repeat your question one more time.
Why does it matter in that these substituents be listed as cis and trans for an alkane?
Because if you misplace it, if you missay what it is, it's going to be wrong because you have to be able to label it because if you don't, you get mixed up, something back can happen.
So why, if I open it up like this, why do I not worry about cis and trans anymore?
Because you see where it is. Because it goes in one direction.
Is there cis and trans here?
No.
There isn't, because there's free rotation around all of these single bonds, right? But there is no free rotation when I make a ring out of it. I can't just rotate around all of those. I can rotate a little, I can wiggle them, but I can't rotate them. I can't rotate completely around that single bond anymore. They get locked into place. Okay. So this is trans when they're on opposite sides of the plane. And that would be cis. What about if we did this carbon up and this number 4 carbon equatorial? Now what is it? Is it cis or trans?
Wait, okay, what's this mean?
Same side.
It's not on the same side.
Oh, you need to flatten it out.
Now if I flatten it out,
See.
right? So it's not always axial equatorial. It depends on where it's located. This is axial, this is equatorial, but these are actually cis to one another. They're on the same side of the plane if I was to flatten it out, right? If I flatten it out, you see that they're on the same side of that plane, okay? This is why models are so helpful. Now what happens if I take this and pull that down and then push that up? What happens?
No, it's this.
The axial and equatorial swaps.
Yeah, but does it change the name, or are they still cis or are they trans?
Still cis.
They're still cis, right? But all I did was make the footrest, the headrest, and so on and so forth, right? Okay. So, cycloalkanes, when you have 2 substituents, actually 2 or more substituents, but for the purposes of this exam, it'll only be 2. You have to be able to name cis and trans, okay? So these red spheres can be anything. A methyl group, an ethyl group, whatever, okay? Now, let's build some more models. Let's get into chapter 4. Chapter 4 is about alkenes and alkynes. And in your model kits, if you have one, you should have a piece that looks like this. And you should have some gray pieces. And if you look on the gray piece, it says sp2. So this is how you build an sp2 carbon. Okay? Just like that. That is a double bond. 2 carbon atoms that are double bound together. Okay? Now, if I take my red spheres and I place them on my alkene, something like that. Okay, so red sphere and red sphere are both on carbon number 1. Do I have cis or trans?
No, it's on the same carbon.
It's on the same carbon, right? Doesn't matter. But what about this?
Trying to be trans.
That is trans because they are on opposite. Notice I can't rotate this to make that without breaking my model, right? This is exactly how a molecule exists. This is how these alkenes work. So I can have this alkene as being a trans alkene or a cis alkene, okay? We can have cis and we can have trans alkenes. We would also call this a disubstituted alkene because the alkene has 2 substituents on it, okay? So we're going to learn about that today. Again, building models is kind of important. If you don't have a model kit, you can go buy a bag of marshmallows and some toothpicks. That works too. And you can have fun eating them while you're, huh?
I had a joke about it. You can't exactly bring it into class without eating it.
Yeah. There's nothing wrong with a marshmallow every now and then. Okay? In fact, if we think about, instead of just red spheres, let's put some real atoms on it. What's the longest carbon chain?
4.
4. So it's a it's a butene. Why is it a butene, not a butane?
This has double bond.
Has a double bond. The functional group for an alkene is the double bond. And we call that an ENE suffix, right? So this is butene. This is what butene?
Wait.
It is trans.
Oh.
Yep. This methyl group and this methyl group are on opposite sides of the double bond.
Okay.
But I can also do this. And that would be cis-2-butene. What's the 2?
That's the location of the double bond.
It's the location of the double bond. I can have 1 butene, which would put the double bond here. That would be 1 butene. Does it have cis and trans?
No.
It does not. Right? You have to have 2 groups, similar groups, on opposite carbons of an alkene to have cis and trans. Okay? Now, what happens if I put a 3rd methyl group on the alkene? So let's say I just put one here. Can I have cis and trans?
No.
I cannot. Because if I do this, this is the same as this. You can't tell that you did anything, right? How would you name that?
I guess it's just gonna be 2-methyl. Wait. 2-methyl. 2-butene.
Really?
I don't know.
Yeah, 2-methyl-2-butene. There is no cis or trans. Doesn't matter. Okay? We call, we call this and this diastereomers of one another. Okay? They're called diastereomers of one another. That's the word up there in the box. We're starting to talk a little bit about stereochemistry. Okay, we've already started talking about it. Stereochemistry just means how things are oriented in space. But what you need to know for right now is that a diastereomer actually has different physical properties. Notice they have the same connectivity. The atoms are connected exactly the same. They have the same molecular formula. It's just how they're placed in 3 dimensions. You've got this versus this. And in fact, this will have a different boiling point. It will have a different melting point than the other one. They have different physical properties. Okay? And that's kind of an important thing. You all know of this, many of you who are in here in nutrition. Trans fats. What does that mean? It means the fatty molecule has trans double bonds. But you also can have cis fats. Which is healthier? Cis or trans?
Cis.
Cis fats are healthier. That's right. That's right. So you've probably heard on television, right? The nasty things that trans fats can do to you, right? Clog your arteries, yada, yada, yada. It's because they have different physical properties.
Yeah.
Trans fats, cis fats, since I've got the cis one up, typically are liquids. Trans fats are typically solids. Solid fats are typically harder on your arteries than liquid fats. Why, I don't know. But that's the case. Okay? So being able to identify cis and trans is going to be important for you. Okay? Now, when we look at the cis and trans molecule, right, we can see the steric interaction starting to happen again, right? The trans alkene is usually the most stable because the big groups are as far away from one another as possible. The cis-alkene, these things are starting to get really close to one another and crowd each other. And we call that steric interaction, right? And so we know that when we have carbons really close together, they like to repel, right? So obviously it's going to be less stable, okay? So cis-alkenes are typically less stable than trans-alkenes. Okay. An alkene has a double bond. What two bonds make up the alkene?
Sigma and pi.
Pardon?
Sigma and pi.
Sigma and pi. What is a sigma bond?
Single bond.
It's a single bond, right? We can rotate around sigma bonds, right? But between these two carbons, there's actually a sigma bond and there's a pi bond. And these models actually don't do you justice with it because it just looks like it's a pi bond,
Yeah.
right? So a sigma bond happens between the two carbons, but each carbon has an unhybridized p orbital, which is represented by these little things here, right? Because it's sp2 hybridized, right? What does sp2 mean? It means you take two p orbitals and one s orbital and make three new sp2 hybrid orbitals, right? The bond between the carbon and the hydrogen is from an sp2 hybridized carbon orbital, an sp2 hybridized carbon orbital, an sp2 hybridized carbon orbital. Well, that leaves the p orbital unhybridized. But this p orbital and this p orbital can actually form a bond. Do you think the pi bond is stronger or weaker than the sigma bond? It is weaker. Can you tell me why by looking at that diagram?
Because it's connected to just the p orbital.
You're close. These p orbitals don't actually overlap completely. It's just the edges of the p orbitals that overlap. The more orbital overlap you have, the stronger the bond. So a sigma bond can overlap very, very nicely and get a nice strong bond. Whereas the p orbital, it's just the edges touching. So while a double bond is stronger than a single bond, the pi piece of that double bond is weaker than the sigma piece. Okay? So very important. These pi bonds typically are fairly weak, and we can actually do chemistry with them, and we're going to talk about that in the next chapter. Okay? It's very important to understand that we can do things with that carbon-carbon double bond, or that pi bond piece, because the bond is weak. Okay? And so this is important for everything that you all do in your studies. If you're studying nutrition, alkenes undergo chemistry in the human body. Fats undergo metabolism. It's all because of the organic chemistry, and it's because of this weak pi bond. Okay? We'll talk a little bit about that as we get into chapter 5. All right. Let's talk about some interesting alkenes. Probably the most well-known and famous of the alkenes is Beta-Carotene. This is the orange pigment from carrots. Why is that important?
Carrots, they're good for your eyes.
They are good for your eyes, but it's not the carrot itself that's good for your eyes. It's the beta-carotene in the carrot, right? It's this molecule, right? This molecule actually gets metabolized and converted into things that you need to see better, right? So you need to have plenty of beta-carotene in your diet. How many alkenes do you see in that molecule?
Alkenes, I see 3.
You see 3 alkenes in this molecule? How many double bonds do we have?
A lot of them.
A lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. We have 11 alkenes, right? This one right here is kind of the magical one. This is where your body actually cuts this molecule in half to help your eyesight. What's the configuration around this? Is it cis or trans? It's trans. This big group and that big group are on opposite sides,
Yeah.
right? So, yeah, we've got a bunch of alkenes in that. You get this from eating carrots, of course. This molecule, zingiberine, I guess. This is oil of ginger. So if you like ginger, you're eating this molecule, and it helps give it the flavor. How many alkenes do we have in this molecule? We have 3. Okay. Now, don't worry about S and R yet. Okay. We'll learn about that, I think, in chapter 6. But the limonene molecules, okay, these come from things like lemons and oranges. Next time you eat an orange, take a piece of the peel and hold it up really close and squeeze it. You'll see a little burst of oil shoot from the peeling. That's mostly limonene. Okay. Does anybody know why the vegetable or the fruits of lemons and oranges produce limonene?
Take the seed
Okay. How? From what?
from thin beans.
It's a very, very good insecticide. And it turns out that it doesn't harm humans. So if you actually go out and buy some organic insecticides, quite a bit of the time they'll contain limonene, and you'll spray it around and it'll kill the bugs. Okay? So it's very good against fruit flies. And so these fruits have evolved to have these to protect them so that the seeds can actually go on and propagate, right? And then this is alpha farnesene. Don't worry about the name. Okay, again, lots of double bonds. This is the molecule that makes the wax on the outside of an apple. Why do apples have waxes on the outside of them? To protect the moisture, right? Moisture to keep it from escaping. That's why apples are so juicy on the inside, because they have this waxy substance that helps coat. Okay, so it helps keep all that stuff in. So that's the waxy coating found on apples. And so here's some just examples of alkenes that you all come into contact with and just never really knew that they were alkenes. Okay. And so limonene actually smells like lemons and oranges. Yeah.
Is the limonene anywhere close to the same thing as lime, like you use in, agriculture?
No. Lime is actually an inorganic material. It's not organic at all. Lime is just calcium carbonate, I believe. Yeah. So I don't know how they came up with the name limonene. I'm assuming something to do with lemons, but I don't know that for sure. All right. So we've already talked about this a little bit, right? That we can rotate around carbon-carbon bonds that are single bonds. We just did the experiment, right, with our model kits. But we can't do this typically in alkenes, because you have the double bond, and that double bond, right, keeps it from freely rotating. I cannot freely rotate around this. However, I will say this, just because you all will learn some of this in biochem, I'm sure, and in some of your, maybe your nutrition classes. We have mechanisms in our body that can convert cis to trans. Okay, there are things that can happen, but it's through a pretty complicated set of chemistries. I can shine a bright light on this and make it go from cis to trans. Okay, and so I don't want you to think that you can't rotate around a carbon-carbon double bond. It's just really difficult to do. Okay, so if I took this and took it out, in the sun for a couple of days, it would eventually go from the cis to the trans. But that's because the light actually breaks the pi bond, allowing it to rotate, and then it reforms. So that's photochemistry that we're not going to get into, but I just wanted you to know that it's not impossible to rotate. You just have to actually do some real chemistry to get it to. Okay? But for the purposes for us, think of these as restricted. Okay? You need to know the difference between the different types of alkenes. We can have monosubstituted. What's an R group?
Group something that can either be anything.
Can it be anything?
Has to have carbons.
It's got to be carbons, right? So for the purposes of this, think of R as just some alkane piece, okay? So monosubstituted alkenes have only one substituent, and they have 3 hydrogens attached to the carbon-carbon double bond. Disubstituted have 2 substituents to the alkene. Now notice here they just show you the 2 substituents on the first carbon. Is that the only way we can do it? Here they show the 2 R groups attached to the same carbon. Is that necessary?
No.
It can either be the same carbon or, you know, one of them on each carbon, right? So you can have, this is disubstituted. If we move this over here, then that would still be disubstituted. If we move that over here, it would still be disubstituted. Trisubstituted, we've got 3 R groups attached to the alkene, and tetrasubstituted, we've got 4 R groups attached to the alkene. All right, so if we look at some examples, okay, how would I name this?
Which one, sir?
Give me the name for it.
How do you name
What would the name be?
it? Well,
One butene.
1-butene. Why? Why not 3-butene?
because if you're going for the parent, it's only 1.
Right, I want a number 1, 2, 3, 4. We want to give the alkene the smallest possible number that we can. So numbering 1, 2, 3 doesn't work, does it?
So alkane gets the biggest one while the alkene gets the lowest.
No, we're always trying to give the lowest numbers to everything in our numbering systems.
Okay.
Even with our substituents in an alkane, we try to give the numbers the lowest possible number for the substituents. Don't confuse the longest chain with the substituents, okay?
Okay.
So this is a monosubstituted alkene. What if we made that a disubstituted alkene?
Then you have to
What would the name be? If I took this and made it a disubstituted alkene?
2
Yeah, 2 what?
try dice.
So if I made this, that's what I've got drawn right there, right? Now if I made it this, now it's disubstituted. Now what's the name? This is 1-butene. What's this? 2-butene? How many think it's 2-butene? Still check it off. Why?
Because
I
it's a
wouldn't give you credit for that. What are we missing?
Well, it's a conformational one.
Okay, so what do I need to name it? Yeah, this would be trans 2-butene.
So trans is different, right?
It is different. What's that one?
6.
That one is cis 2-butene. So you'd write cis 2-butene. Okay? All right. Let's see. So here's some examples of naming alkenes, right? So you can see the bond line drawings and you can see the condensed formulas, right? So we have 1-hexene, not 5-hexene. We have 4-methyl 1-hexene. Right, there's the longest chain. We've got a methyl group hanging off of that, right? And we're going to number this. The alkene has to be part of the longest chain. That's one of the rules. So this is a pentene molecule, so it's 1-pentene, right? So I have 2-ethyl, 3-methyl, 1-pentene. What does that 1 tell me? It tells me where the double bond is located, okay? All right, let's skip that one because we've already talked about cis and trans. Cis and trans doesn't always work. Cis and trans really only works if you have only 2 substituents that are similar, right? This and this are similar. Actually, they're identical in this case. Cis and trans works. But what do you do when you have a tetrasubstituted or trisubstituted double bond where things can either be similar or different? We have to use what's known as the EZ configuration, E or Z. It comes from the German. Z means, well, there's the word, zusammen. It means on the same side. The way that I remember it, it's easy. Z is on the same side. Okay? Think about that. E, entgegen, I think I'm pronouncing that right. It's German for opposite. Okay? So let me do this in black. So let's have a carbon-carbon double bond. Is that cis or trans?
We can't say.
You can't say. But you need to be able to know how to put all those substituents on there, right? When you're faced with something like this, you look at each carbon atom of the alkene and you assign priorities to the substituents. And you assign priorities based on atomic number. On the exam, I will give you a copy of the periodic table. Okay? What do I know about the atomic number of bromine relative to chlorine? Which one's higher?
Bromine.
Bromine, right? So this one gets high priority. This one gets low priority. Carbon versus fluorine, which one has the highest priority? So this is high. This is low. So the highs are on opposite sides.
So it's E.
It is E. So this is the E alkene. Yeah.
For the CH3, are you giving it low based off of the carbon? or based
The
off-
carbon. Yes. So you always look at the first atom to start with. But you bring up a good question. What if the first atom is the same on both of them? So let's look at another example. Let's do this where we will.
So the high and the low, is it, you said based on the atomic number, the one that has a larger atomic number?
Yep.
The atomic number is the number written underneath it.
The atomic number is on the periodic table. It's the placeholder on its
Oh, so it's like electronegativity.
kind of, yeah.
Okay.
But it's the number of protons, right? And-
Yeah.
Yeah. So we can make a choice here, right? We know that bromine has higher priority than chlorine. This is carbon, and this is carbon. How do I make a decision now?
Atomic mass?
Almost, but not quite. We start to look at what else is attached to that atom,
Right.
right? So I can't make a decision looking at these atoms, but what else is attached to this?
Hydrogen.
H3.
3 hydrogens, right? What else is attached to this?
One carbon and 2 hydrogens.
1 carbon and 2 hydrogens. Which one wins?
1 carbon and 2 hydrogens.
Carbon is always higher priority than hydrogen, right? So this would be high, and this would be low. So again, it would be, well, you name it. Name it for me. Take a moment.
I did the first one.
You want us to name it?
Yeah, name it.
I know it starts with an E.
I guess it's E, 1 bromine, 1 chlorine,
1 bromine, bromo,
bromo, 1 chloro, 2 methyl. Okay, it's alphabetically in order.
is it 2 methyl?
Isn't there an ethyl in
Well, the ethyl becomes part of the parent chain.
There's the parent. And the parent's what? 1, 2, 3, 4, right?
1 butene. That's long.
That's long. I'm not going to give that to you on an exam. Okay? But that would be the E configuration. And then actually, I missed, the E needs to be in parentheses. That's the rule. And it needs to be in italics. Okay? And I can't write italics, so it is what it is. Okay. All right. I want you all to take about 10 minutes. Get with your friends. Don't do D. Work A, B, and C in groups. Break up in groups and give it a shot.
So you said that bromine due to the electronegative is.
Has to do with its atomic number.
Okay.
Bromine's further down on the periodic table than chlorine.
What is the line in the double bond and the C?
This, that was my, that was when I was searching.
And this is, so after the class over, you make this public, we post it on our Canvas thing? Because you're going to write for me to be writing. Can't write it fast.
That's okay. I publish all these things every day.
Outsourced this morning, so this will be hard for me to do that. It's not gonna be there.
Like this. Yes, I think I like it.
I can see why you emphasize us studying the names.
Work with somebody.
So we got that one that's high. I need to
We prioritize the numbering, meaning the lowest number for the location. So it's way easier than alkenes.
this one. That would be high.
Where that in this one, this double one here to this one. Yeah. That's it. Yeah. And we start listing the constituents and constituents. So it's gonna be this one fluoro because it's alphabetically organized. That is CNS. I just do one fluoro. I usually do the like E or D or and then the location of the double bond. The last one, you find the double bond, we take it. And then we gotta figure out the whatever it is. I think cis or trans because we are not saying except for the short C, it's gonna be much easier to write it out. So I think And so we can decide whether to use CCD or this method. Yeah, this.
These two are the same things, two are different.
Right, well, we can not use this for trends because there are, it's, what do you call it? This tetrasubstituents, meaning all of the 4 branches have carbons in it. So we can't use this as trends. It's just gonna be E or C, right? So we determine which one is the higher, what has the higher atomic number, higher priority, I guess. So we can start from the last one. So we got these 2. This one is definitely higher. This one lower. Oh, this is the higher priority of science. So is that a European? Yeah. So it's just E interacted 4. That's it. Okay.
I never know what number to start with.
You want to try to do the second one? It's quite fun.
It would be
I feel like this would be fun once you kind of get the hang of it.
It's clear which one's the parent chain.
Yeah. And you want to put these in alphabetical order.
Right. So Roman is first. Yeah.
Okay, so since there's none of the chloride or chromium in that what would we do?
It's pro. Yeah.
I was gonna say propo, but that's
So
fine.
if it's an alkene, then it
Is it propene or propo?
Okay, that should be all. Now,
You want?
yeah.
But these two middle C's would be
Okay, so the way I would, it's definitely using E or the H because it clearly has three constituents like carbon, this chlorine, this bromine. But then you might not notice that the other one's actually hydrogen. And you can see, so from here we can easily determine which one has the higher priority. Well, in the family it's FCLBRI, so it's going to be the lower you go in the period, the more atomic number. So it's going to be BR.
We go.
Yeah. Yeah. You did great.
I know, it's
I'm so good then.
Yeah, it's like
Since that one doesn't have any like extra, that would.
Isn't E on the same side?
Z is on the same
Like,
side.
cause there's not like a CO or there's nothing labeled, so it's all carbon.
Well, not necessarily.
Okay.
If the number of carbons are different, not symmetrical, then you can't.
All right. Let's come back together.
Pretty sure you can do it.
Thank you.
So on A, what's the first thing that we have to do?
Find the highest one.
No.
The highest what?
Or the one who has the highest payoff number.
Well, not yet. We're naming, right? So what's the rule of naming? We always start with finding the longest parent,
Parent chain.
right? So what's the longest parent chain here?
5.
1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Yeah, so 5. So this is going to be what kind of a parent?
Pentene.
Pentene, because it's an alkene, right? All right. So now we have to look at both carbon atoms of the alkene, and we have to assign priorities, right? So that we can figure it out. So I've got, if I look at this, I've got a CH3 and I've got a CH2CO. Which one of these is the highest priority?
CO.
This one, that's right. So this is high and this is low.
And it'll be E.
Well, we've only done this one carbon,
The other
right?
one.
I've got high and low. Now I got to figure this one out, right? Which one's high, which one's low? What's this one?
That's higher.
This is high and this is low, right?
Yeah.
So wait, it's still the same element, why the lower?
Well, it's the same element, but we can't make a decision, right? Carbon versus carbon, I can't make a decision. So I have to look at the next element. What's attached to this? Just hydrogen. What's attached to this? Another carbon.
So if they both equal, if they both say you look at what they are attached to.
You have to go out further, that's right. So this is going to be high, and this is going to be low. So high and high are on
Same
the same side? Same or opposite?
opposite.
Opposite.
They're opposite. So it's going to be an E, right? So when I name this, I'm going to find that it's E. 1 chloro, 2, 3 dimethyl, 2 pentene. So which way did I number? Did I number this way or this way?
From the left to the right.
I number from left to right. Now wait a second. I just told you that 5, 1, 2, 3, 4, 5, but I can also have 5 here. 1, 2, 3, 4, 5. Why did I pick this one?
Because it's
Why did I pick this chain as opposed to this chain?
has a higher payout number.
Okay,
Ah.
but why? You're right, but why? Why didn't I name it this way? What do we know about substituents? What do we want substituents to be?
The lowest possible number.
We want them to be the lowest possible number, and we always want to pick the chain that gives us the most substituents, don't we? So if I pick this, chlorine becomes a substituent, right?
Yes.
And it would also have the lowest possible number. So that's why. Okay. How about the second one? Which one of these is highest or the lowest?
So it'll be higher.
Bromine is high, chlorine is low. What's on this carbon?
Carbon.
Hydrogen.
Carbon and what else?
Hydrogen.
And a hydrogen. So which one's high?
Carbon.
All right, so I've got high and high. So what is this?
Z.
Z. And what's the parent?
Pentene. Wait, propene.
How many carbons are in the longest chain?
3.
3, right? So this is Z, because these things are on the same side, right? 1 bromo, 1 chloro, 1 propene. In the book, they didn't actually put the 1 for propene. Why can you get away with it here without listing the 1 here? I did it because it's the most accurate way to represent it. But why would this just be as accurate as Z, 1 bromo, 1 chloro, propene? Because the 1 bromo and 1 chloro define carbon number 1.
So can you explain again the high and low, please? Because
Sure. So let's look at this one. Let's draw it out. Chlorine and bromine. So you look at the things that are attached to each carbon of the alkene. So let's look at this one. I've got chlorine and I got bromine. Which one has the highest atomic number? Bromine. So this is high. This is low. Which has the highest atomic number, hydrogen or carbon?
Carbon.
That's right. So this is high, and this is low. So that's how we assign the priorities. And since my highs are on the same side, it's Z. Yeah, it's Z. It is Z. How about C?
So we're looking at the sides, like on the other sides of the double bond, right?
So think of
Okay, that's what I.
think of the carbon. We know that the carbon-carbon double bond can't rotate, right? So if you think of this as the plane, My highs are on the same side of that double bond. That's why it's Z. Yeah.
How do you know to put the 2 in front of the pentene, like the 1 in front of the
Okay, so I can number 1, 2, 3, 4, 5, or I can number 1, 2, 3, 4, 5, and we want the alkene to have the lowest number, right? So I can number it as 1, 2, or I can number it as 1, 2, 3. Well, 2 comes before 3, right? So this is why I get the number 2. That tells me where in this longest chain my carbon-carbon double bond is. That make sense?
What about the, chloro or bromo, is it, you put the 1 before the chloro because it's on the first carbon?
It is, right? This is carbon number 1, 2, and 3. But I can also draw it now. How would I name it? It's the same molecular formula. I just swapped this hydrogen and this chlorine. I just swapped positions, right? So we got to assign priorities. This is high. This is low. This is high. This is low. When I think about this plane, my highs are on opposite sides. So it's E. E what?
1 bromo.
E1 bromo.
1 chloro. 2 chloro.
2 chloro.
1 pentene. No propene. My bad.
Yep. How about C? What's the longest chain?
7. Heptene.
7, so it's going to be a heptene parent, right? I got to determine priority here, right? Which one of these is higher priority, this group or this group?
Del bromo.
So this is high, this is low. How about here?
The lower one.
Low and high, right? So I've got high and high on
Opposite.
opposite sides, so it's going to be a
E.
E, right? It is E, and when I do the numbering, I'm going to 1, 2, 3, right?
Right.
So here's my parent. What are my substituents? They're all methyl groups,
Right.
and I've got 3 of them. So it's E, 2, 3, 4, trimethyl, 3 heptene.
Can you do that again with the high and the low one?
Sure. So if I look at this carbon, it's attached to a carbon and a carbon, right? So I can't make a decision just based on the first atom. But this carbon is attached to 2 hydrogens and another carbon. This one's only attached to 3 hydrogens. So this is higher priority than this.
Why are you using, carbons, not really in the middle, but towards the, it's not at the very end?
What are you talking about?
So say with the first high is on the left,
Uh-huh.
right there, why are you using that carbon and not the?
Because that's what's attached to the alkene. You always look at what's attached to the alkene.
Oh, okay.
Yep.
So that carbon is attached to another carbon?
It's attached to 2 hydrogens and a carbon.
Carbon, is that,
That one's only attached to 3 hydrogens.
you're looking at the bottom bond, or the one in, yeah, you look at the bottom, there's
Yeah.
the hydrogen?
So you ask yourself what's attached to this. It's this group, and this one has the higher priority. Okay? Yeah.
Like the X thing,
Could I what?
can you draw it out? Number C.
Draw it out.
C? All right, so we got. And what do you want me to do?
So we have the CC double bond and then how you were explaining the high and the low.
Okay, so this is the CC double bond, right? And there's my plane. I draw a line through the carbon-carbon double bond. I look at this carbon atom and ask myself what's attached to it. I've got a carbon atom and I've got a carbon atom. I can't make a decision yet. This carbon atom is attached to 3 hydrogens. This carbon atom is attached to another carbon and 2 hydrogens. This takes priority, so this is high. And this is low. Does that make sense? Here I've got a CH3, here I've got a CH that's attached to 2 other carbons, so this is high, and this is low. My highs are on opposite sides, so it is. And then when you circle the longest chain, right, you'll see that there's a methyl group, and a methyl group. Those are the substituents.
Wait, why is the top one low?
This one?
Yeah,
Because it's a CH3.
and isn't the bottom one also a CH3?
No, it's a CH.
Oh, that's before the CH. Okay.
Yeah. Look at the atom directly attached to the alkyl. All right. In your model kit, if you have one, you'll have a piece that looks like this. This is an alkyne. Each one of these points that I'm pointing to with my fingers right now are carbon atoms. That's a carbon, and they're triply bonded. And it's linear. An sp hybridized carbon is straight, or carbon-carbon bond is straight. 180-degree bond angles, okay? So you've got p orbitals that are in the plane of the board that are overlapping, and you've got p orbitals that are coming in and out of the board at 90 degrees to one another. Yeah.
I don't have that model one, but mine have like the ball and stick one.
Yep.
Can I make that?
Yeah, you can. So you should have. So what you do is you use your carbon, and then you have to put 3 bonds between the carbons. So it's a,
Is it the big ones or the small
these
ones?
are big bonds.
3 big ones, or is it 1 small one and 2 big ones? 'Cause one's
Yeah,
like a
right.
large system.
Are these the same size? There should be some instruction. Just use the 3. Is an alkyne, that's what we call it, an alkyne. So we have alkanes, which are all single bonds. We have alkenes, which have double bonds. And we have alkynes, which are triple bonds. Is this saturated or unsaturated?
Unsaturated.
It is unsaturated, right? It is very unsaturated. It has bond angles of 180 degrees, as I mentioned. There are some interesting alkynes that you probably have come into contact with, okay? If you've ever done oxyacetylene welding or cutting, you've used alkynes. You've used acetylene. It's the simplest alkyne. It's C2H2, okay? It's a colorless gas. It burns an oxygen, forms carbon dioxide and water, and gives off lots and lots of heat. And so you can cut through thick pieces of steel or weld them together. Here they're cutting a piece, what appears to be a piece of railroad iron with an oxyacetylene torch, okay? It makes a very good fuel for that kind of thing, okay? There are alkynes in synthetic hormones. So here's an example of an oral contraceptive, okay? 2 of them. And what you can see in both the cases is that they have a carbon-carbon triple bond. If you get rid of that carbon-carbon triple bond, the medicine don't work, okay? And that's not a good thing, right? So these are synthetic hormones that are used in oral contraceptives. Here are the naturally occurring hormones. And what you can see is that they look very similar, except right here. they've put a carbon-carbon triple bond. Okay? And so you'll find a lot of carbon-carbon triple bonds in a variety of medicines, and I just used an example of hormones here for this one. Okay? Here's an example of the toxin in poison dart frogs, right? So why do they call them poison dart frogs? Because people will take a dart, rub the dart on the frog, and then when you stab somebody or an animal with it, it injects the poison that's very, very toxic, and it kills the prey. Okay? Where is the carbon-carbon triple bonds? There's one right there. There's one right there. What about this?
Double bond.
It's a double bond. So this is a molecule that has an alkyne, 2 alkynes, a couple of alkenes. What's this functional group?
Alcohol.
As an alcohol, and what's this one?
Amine.
An amine. All of these functional groups are coming together to create this poison dart, if you will, poison dart molecule. And here's an example of a ball and stick model, building it all out. You can see how things are starting to get pretty crammed. But that is a poison dart frog. You probably learned in your basic biology class, anytime you see a very brilliantly colored frog, stay away from it. Very, very toxic. Okay, these are poison dart frogs. Okay. One of the things that is important about alkynes is they have this unusual ability to function like acids. Okay, so we can have an alkyne that has a terminal hydrogen, we say. Okay, so just some R group. If a hydrogen atom is attached to a carbon-carbon triple bond, or carbon that's triply bonded to another carbon, this hydrogen is acidic. It has a pKa of about 25. Now wait a second, is that really a very good acid?
Yeah.
It's not a very good acid, but in organic chemistry terms, it's extremely acidic. Acidity is all relative. Depends on what you're talking about. Okay? And it turns out that if I can react this with a very strong base called amide, usually sodium or potassium amide, it's NH2 minus. This is a very strong base. It has a pKa of about 40 something. I don't remember it right off the top of my head. It will abstract that proton and generate what's called an acetylide anion. And we'll talk about the importance of these in later chapters when we start talking about real reactions. Okay? But this carbon is now negatively charged. Why is it negatively charged? We broke a bond, that's true. How do I figure out that charge?
Formal charge.
Yeah, I circle it, right? So how many does carbon come in with?
4.
How many does it formally own right now? 5. 1, 2, 3, 4, 5, right? So it's a negatively charged carbon atom. Okay? Very useful to have negatively charged carbon atoms. Notice the equilibrium lies to the right. The equilibrium constant is 10 to the 13th. That means it goes to completion. There's essentially, when you do this reaction, there's none of this left. It all becomes product. Okay? What can you tell me about that? What is the Lewis acid on this side? Acetylene. What's the Lewis base? All right. What's the conjugate base? And the conjugate acid? Ammonia. Notice I go from a pKa of 25 to a pKa of 38. So I've gone from stronger acid to weaker acid. That equilibrium always favors the weaker acid. Okay? And the difference here is very large. That's why I have a KEQ of 10 to the 13th. Okay? Now, let's use another base. What other bases do you all know of that you used in Gen Chem?
NaOH. Sodium hydroxide.
Yeah, let's look at what happens if we tried this with sodium hydroxide. Okay? Notice the equilibrium is lying over here. This essentially doesn't happen. Why? This is the weaker acid. This is the stronger acid. The equilibrium never favors the stronger acid. It favors the weaker acid. Okay? So If you can identify the acids and the bases, you can determine roughly where the equilibrium is going to lie. Okay, and so what you see if you look at hydrocarbons, you'll see that alkanes have a pK of about 50, 51. They're not acidic at all. Alkenes have a pKa of 44. Alkynes have a pKa of 25. So alkynes are the strongest acids of the hydrocarbons. Okay? Only carbon and hydrogen. So what effect is at play here? Why is this more acidic than this?
The orbitals, it's closer.
Okay? We learned about several effects. We learned about the element effect. We learned about what? Resonance effect. We learned about, pardon? Inductive. And we also learned about hybridization effect, right? What's the hybridization of this carbon? sp3? sp. sp, the electrons can actually get closer to the nucleus because they have more s to them, right? And so you end up with a very, relatively speaking, strong acid compared to the others. All right? All right, we are going to pick up with this on Wednesday with getting into Chapter 5. We're going to start talking about some reactions. We'll take it kind of easy on Wednesday. No quiz today, but have everything ready for Wednesday.
So we should be looking to do chapter 3, chapter 4, chapter 5.
What chapters does exam on cover?
Exam covers up through what we cover on Wednesday. So if we don't finish it all,
So the next quiz is going to be either 3, 4, 5.
pardon?
The quiz is going to be from 3, either from 3 to 4 to 5.
It's pop quiz. You got to have all your work done. I can ask any of them.
So do them all.
Do them all.